There's a quiet rebellion happening in the far reaches of the cosmos, places where the universe throws the rulebook out the window and dares to rewrite reality itself. Picture this, a black hole so massive it warps time into a slow-motion spiral, or a nebula where matter appears and vanishes like a cosmic magic trick. These aren't scenes from science fiction. They're real, mind-bending corners of space where the laws of physics don't just bend, they shatter. And today, we're setting off on a journey to uncover 30 of these extraordinary phenomena, each one more bewildering than the last. Think about the rules that govern our everyday world. Gravity keeps us grounded, time moves forward, and matter can't just disappear. But out there, in the vast expanse of space, these rules crumble. Imagine standing on a planet where the sky burns with twin suns, casting shadows that defy logic, or floating near a singularity where light itself is trapped in an endless loop. These aren't just anomalies, they're cosmic puzzles that challenge our very understanding of existence, and the deeper we look, the more we realize how little we truly know. This isn't just a tour of strange places, it's an invitation to rethink reality. Every discovery we'll explore today pushes the boundaries of science, forcing us to ask, what if everything we've been taught about the universe is just the tip of the iceberg? From wormholes that might be secret shortcuts through space to stars that pulse with rhythms we can't yet explain, each stop on this journey will leave you questioning the nature of the cosmos. So settle in, because by the time we're done, you'll never look at the night sky the same way again. The universe is far stranger, far more mysterious than we ever imagined, and it's time to see why. Our first stop takes us to one of the most unsettling places in the known universe, a sprawling abyss so empty it feels almost unnatural. Known as the Boötes Void, this colossal region stretches over 330 million light-years across, a staggering void where galaxies should be clustered by the thousands. Instead, you'd find only a handful scattered like lost travelers in an endless desert. Astronomers call it the Great Nothing, and for good reason. It defies everything we thought we knew about how matter is distributed in the cosmos. What makes this void so baffling isn't just its size, but the sheer improbability of its existence. In a universe where galaxies tend to clump together like cities connected by cosmic highways, finding a gap this vast is like stumbling upon an ocean without a single drop of water. Some scientists argue it could be a statistical fluke, a rare but possible quirk in the grand tapestry of space. Others whisper about darker possibilities. Could this be evidence of forces we don't yet understand? One radical theory even suggests an advanced civilization might have manipulated dark energy, harnessing it in ways that left behind this eerie, hollowed-out stretch of the cosmos. But here's what really sends chills down the spine. The Boötes Void isn't just empty, it's too empty. Even the sparse galaxies within it seem oddly isolated, as if something or someone has been clearing the stage. And that raises a haunting question. Is this just a strange accident of nature, or a cosmic clue pointing to phenomena beyond our current grasp? Standing at the edge of this void, we're forced to confront how much of the universe remains hidden in shadow, and how little we truly understand about the rules, or lack thereof, that govern the deepest reaches of space. If the Boötes Void left you questioning the universe's rules, brace yourself. Our next mystery dives into an even deeper cosmic conundrum. Picture throwing your most precious book into a fire, watching the pages curl into ash. Now imagine if someone claimed they could reconstruct every word just by studying the smoke. That's essentially the puzzle physicists face with black holes, where the laws of quantum mechanics and Einstein's relativity collide in what's known as the information paradox. At the heart of this mystery lies Stephen Hawking's groundbreaking discovery. Black holes aren't eternal. They slowly leak energy, evaporating over eons through what we now call Hawking radiation. But here's the catch: quantum physics insists that information, like the details of what fell into the black hole, can never truly be destroyed. So where does it go when the black hole vanishes? Either our understanding of quantum mechanics is flawed, or Einstein's theory of gravity is missing a critical piece. Recent breakthroughs offer a tantalizing clue. Some theorists suggest the information isn't lost at all. It's smeared across the black hole's event horizon like a cosmic fingerprint, preserved in a holographic imprint. Imagine the surface of the black hole acting like a scrambled hard drive, storing data in ways we're only beginning to decode. Others propose even wilder ideas, like hidden parallel universes or microscopic wormholes ferrying information to safety. Yet for all the theories, one thing is clear: this paradox forces us to rethink the very fabric of reality. If information can escape a black hole's grip, what other cosmic rules might be illusions? Every time we peel back one layer of this mystery, another, even stranger question takes its place. And that's the beauty of the universe. It doesn't just break the rules. It rewrites them. Just when you thought the cosmos couldn't get any stranger, along comes a phenomenon so puzzling it makes black holes look downright predictable. Imagine the entire universe as a vast river, with galaxies not just drifting apart as space expands, but all mysteriously pulled in the same direction, as if caught in some cosmic undertow. This isn't science fiction. It's called dark flow, and it's one of the most tantalizing mysteries in modern astronomy. The story begins with clusters of galaxies, not just a few, but thousands, all moving toward a single point in space at speeds that defy explanation. We're not talking about a gentle nudge. These galaxy clusters are racing at over 2 million miles per hour towards something we can't see, something beyond the edge of the observable universe. And here's the kicker: according to everything we know about the Big Bang and the distribution of matter, this shouldn't be happening. The universe is supposed to expand uniformly, with matter spreading out evenly in all directions. But dark flow suggests there's a colossal something out there exerting a gravitational pull so immense, it's tugging on entire galaxy clusters like a hidden magnet. So what could possibly be powerful enough to move galaxies? One theory points to an unimaginably massive structure lurking in the unobservable universe, perhaps a supercluster of galaxies so dense it warps space-time on a scale we've never seen. Another, even more radical idea, that we're feeling the gravitational influence of another universe entirely, a neighboring cosmos in the multiverse brushing up against our own. Picture two soap bubbles floating close together, their surfaces subtly deforming each other's shape. If true, dark flow could be our first glimpse of a reality beyond our cosmic horizon. But not everyone's convinced. Skeptics argue it could be a measurement error or an artifact of how we map cosmic microwave background radiation. Yet each new study seems to deepen the mystery. One team found the flow extends even farther than previously thought, suggesting whatever's pulling these galaxies isn't just powerful, it's staggeringly distant. Here's what makes dark flow so thrilling. It doesn't just challenge our understanding of the universe. It hints that reality might be far grander, far stranger than we ever dared imagine. Whether it's evidence of a multiverse or some undiscovered cosmic structure, one thing's certain: the universe still has secrets it's not ready to give up. And that's what makes the hunt so exhilarating. Now let's turn our attention to one of the universe's most extreme laboratories, a place where matter is pushed to its absolute limit, creating conditions so bizarre they seem ripped straight from the pages of a sci-fi novel. Neutron stars are the collapsed cores of once massive stars that didn't quite become black holes, but what they lack in darkness, they make up for in sheer, jaw-dropping weirdness. Take a single sugar cube's worth of neutron star material. On Earth, it would weigh as much as 1 billion tons, roughly the mass of every car in the United States crushed into a space smaller than your fingertip. That's because these stellar remnants are so dense, their atoms have been obliterated. Protons and electrons are squeezed together until they merge into a sea of pure neutrons, packed tighter than anything else in the known universe. But the strangeness doesn't stop there. The surface of a neutron star isn't just hard, it's 100 billion times stronger than steel, forming a crust so rigid it can crack under unimaginable stress, sending ripples through space-time itself. Yet despite this incredible solidity, some neutron stars spin at dizzying speeds, rotating hundreds of times per second. These pulsars act like cosmic lighthouses, beaming radiation across the galaxy with such precise regularity that astronomers once mistook their signals for alien transmissions. And then there's time. Get too close to one of these ultra-dense objects, and gravity warps the very fabric of reality. A clock on the surface would tick noticeably slower than one in deep space, a real-world example of Einstein's time dilation taken to the extreme. Some neutron stars even have mountains, though you wouldn't want to climb them. These peaks are barely a few millimeters tall, yet contain more mass than entire mountain ranges on Earth, compressing spacetime so severely they create gravitational echoes detectable across interstellar distances. But perhaps the most mind-bending feature of all is what happens when two neutron stars collide. The resulting explosion, a kilonova, is so powerful it forges heavier elements like gold and platinum in an instant, scattering them across the cosmos. Every piece of jewelry on Earth likely contains atoms born from these cataclysmic crashes. Neutron stars don't just bend the rules of physics, they rewrite them entirely. They're proof that the universe has a flair for extremes, crafting objects that challenge our very understanding of matter, gravity, and time. And with every new discovery, we're reminded that the cosmos is far stranger and far more inventive than we ever imagined. Rising like twin titans from the heart of our galaxy, the Fermi Bubbles defy explanation, two colossal geysers of gamma-ray energy stretching 25,000 light-years above and below the Milky Way's disk. Discovered just over a decade ago, these towering structures glow with the energy of 100,000 supernova, yet their origin remains one of the most heated debates in astrophysics. Imagine standing on a planet halfway across the galaxy and still seeing these bubbles as towering pillars in the sky, a silent reminder that even our familiar cosmic neighborhood holds violent secrets. The scale alone is staggering. Each bubble could swallow our entire solar system 1,000 times over, their edges crackling with particles moving at nearly the speed of light. But here's the real puzzle. These aren't remnants of some ancient explosion. They're active, dynamic structures, suggesting whatever created them isn't just a relic of the past, it might still be happening. One leading theory points to Sagittarius A, the supermassive black hole at our galaxy's center. Astronomers speculate that millions of years ago, it might have gorged on an enormous meal of gas and stars, belching out these bubbles in a cataclysmic eruption. Picture a sleeping dragon briefly waking to spew fire into the heavens before dozing off again. Yet there's a twist. Some researchers argue the bubble's energy signature doesn't quite match what we'd expect from a black hole outburst. Instead, they propose something even more exotic, dark matter particles annihilating each other in invisible fireworks. If true, these bubbles could be our first tangible glimpse of the universe's most elusive substance, a shadowy process playing out on a galactic scale. What's truly humbling is how recently we spotted them. Hidden in plain sight, the Fermi Bubbles were only revealed by cutting-edge gamma-ray telescopes, proving that even our own galaxy can keep monumental secrets. They challenge our assumptions about how galaxies evolve, reminding us that the cosmos doesn't just follow tidy rules, it leaves behind enigmatic monuments to its own chaos. And with every new observation, we're left wondering what other colossal structures might still be lurking, undetected, in the depths of space. Somewhere in the inky blackness beyond our galaxy, an unseen leviathan tugs at the cosmic strings, a gravitational behemoth so powerful it's dragging the Milky Way and millions of other galaxies toward it at 14 million miles per hour. Astronomers call it the Great Attractor, and it's one of the most perplexing mysteries in modern cosmology, hidden behind thick veils of interstellar dust in the constellation Centaurus. This invisible titan possesses the mass of 100 quadrillion suns, warping the very fabric of the universe around it. Yet despite its staggering influence, we've barely glimpsed what it actually is. For decades, scientists puzzled over why our local group of galaxies seemed to be racing toward this uncharted region of space. The first clues came in the 1970s when astronomers noticed galaxies in our cosmic neighborhood weren't just drifting apart with the universe's expansion. They were all streaming toward the same point like leaves caught in a celestial current. The discovery upended our understanding of large-scale cosmic motion. Normally, galaxies move in predictable patterns dictated by the universe's expansion and the gravitational pull of nearby structures. But the Great Attractor defies those expectations, acting like a cosmic magnet with a pull so strong it overrides even the relentless stretch of space-time itself. So what could possibly exert such unimaginable gravity? One leading theory suggests it's a supercluster of galaxies so densely packed, its combined mass creates a gravitational vortex. The Norma cluster, a massive gathering of galaxies near the suspected epicenter, might be part of this structure, but here's the catch. Even if we account for all the visible matter there, the math still doesn't add up. The Great Attractor's pull is far stronger than what we can observe, hinting at vast amounts of hidden dark matter weaving an invisible web of gravity. Yet some researchers propose an even wilder possibility, that this isn't just a cluster of galaxies at all, but a rare kink in spacetime itself. Imagine the universe as a stretched bedsheet, with most objects creating gentle dips. The Great Attractor in this scenario might be like a sudden fold in the fabric, a cosmic wrinkle so steep it warps everything around it. If true, it could mean we're witnessing a flaw in the very geometry of reality, a place where Einstein's equations break down in ways we don't yet understand. The irony, we may never get a clear view of it. Our own galaxy's dusty disk blocks much of the light from this region, leaving astronomers to piece together clues like detectives reconstructing a crime scene from shadows. New radio telescopes and infrared observatories are finally piercing that veil, revealing hints of immense structures previously obscured. But with every answer comes fresh questions. Is the Great Attractor itself moving towards something even larger? Could it be part of an unfathomably vast cosmic flow, like a single whirlpool in a much greater current? What makes this mystery so thrilling isn't just the scale, it's the reminder that even the mightiest forces in the universe can remain hidden in plain sight. The Great Attractor humbles us. It whispers that for all our telescopes and theories, the cosmos still holds cards close to its chest. And as we strain to see through the galactic dust, one truth becomes clear. The universe doesn't just contain mysteries. It is one. If the Great Attractor shows us how gravity bends the universe on colossal scales, then quantum foam reveals a reality far stranger, where even empty space isn't truly empty. Picture the fabric of spacetime not as a smooth, unbroken sheet. but as a seething, turbulent ocean where unimaginably tiny bubbles of energy constantly form and vanish. At scales a billion times smaller than an atom, the vacuum of space crackles with activity as fleeting pairs of particles and antiparticles flicker into existence for mere fractions of a second before annihilating each other. This isn't theoretical speculation. It's a fundamental prediction of quantum mechanics, confirmed by delicate experiments measuring forces like the Casimir effect. But here's where it gets wild. This quantum foam isn't just background noise, it suggests space-time itself might have structure, a frothy, chaotic underbelly where the very concepts of here and now break down. Imagine zooming in on the surface of a calm pond until you see it's actually made of countless, ever-shifting bubbles. Now replace that pond with the fabric of reality, and you've got a glimpse of the universe's most frenetic dance floor. Some theories propose that within this foam, microscopic wormholes could spontaneously form, threading space with tunnels that might connect distant points or even different times. The implications are staggering. If space-time is this malleable at the tiniest scales, could advanced civilizations someday learn to stabilize these fleeting structures? Imagine harnessing quantum foam to create shortcuts across the galaxy, turning what's now science fiction into engineering. But there's a catch. The energy required to manipulate space-time at this level would dwarf anything we can produce. The foam's bubbles exist on scales so small, probing them directly would need particle accelerators the size of solar systems. Yet the foam's existence hints at deeper mysteries. Some physicists argue it could be the key to unifying gravity with quantum mechanics, a puzzle that's eluded science for a century. Others wonder if these quantum fluctuations might explain dark energy's push on the cosmos. And lurking beneath it all is a humbling truth. Even the emptiness of space is alive with possibility, a reminder that the universe is far more dynamic and far less predictable than it appears. Even the most fundamental assumptions about our universe can be upended by a single, stubborn anomaly, and few are as baffling as the so-called axis of evil. This isn't some cosmic supervillain's lair, but a mysterious pattern etched into the oldest light we can observe, the cosmic microwave background, the afterglow of the Big Bang itself. Stretching across the sky like a faint fingerprint, this relic radiation should be evenly speckled with hot and cold spots, a random mosaic reflecting the universe's infancy. But instead, scientists found something shocking. These temperature fluctuations aren't scattered chaotically. They align along a specific axis, as if the universe has a hidden compass pointing toward something we can't see. The implications are staggering. For over a century, cosmology has relied on the cosmological principle, the idea that the universe is uniform in all directions, with no special place or orientation. It's the foundation of everything from Einstein's equations to our models of cosmic expansion. Yet the axis of evil blatantly defies this, suggesting the early universe might have had a preferred direction, a cosmic tilt that shouldn't exist. Imagine spinning a globe and discovering all the continents secretly face the same way. That's the level of paradox we're dealing with. Some researchers argue this could be a statistical fluke, a trick of perspective like seeing faces in clouds. But the odds of such an alignment happening by chance are astronomically low, less than 1 in 10,000. Others propose more radical explanations. Could it be evidence of a pre-Big Bang structure, some imprint from a prior universe that bled into ours, or perhaps the gravitational tug of a neighboring universe, warping space-time like a hand pressing against fabric? The wildest theories even flirt with the idea of a cosmic defect, a crack in the geometry of reality left over from the universe's birth pangs. What makes this mystery so electrifying isn't just the science, it's the philosophical earthquake it triggers. If the universe does have a preferred direction, it means our place in the cosmos might not be as ordinary as we thought. We could be living in a skewed pocket of existence like ants on a tilted table, oblivious to the slant. And that raises a haunting question: how many other fundamental truths about reality might be waiting to unravel? The axis of evil doesn't just challenge our models, it dares us to imagine a universe far stranger and far less predictable than we ever dreamed. Black holes dominate our cosmic nightmares, regions where gravity wins so completely, even light can't escape. But what if the universe has a way to fight back? Enter white holes, the hypothetical twins of black holes that spit out matter and energy with unstoppable force instead of swallowing them. While black holes pull everything past a point of no return, white holes would violently repel anything trying to cross their threshold, like a cosmic fountain erupting endlessly into space. The math suggests they should exist. Einstein's field equations, which describe the curvature of space-time, actually allow for white holes as valid solutions, essentially black holes running in reverse. Imagine pressing rewind on a black hole's life cycle. Instead of collapsing inward, a white hole would explode outward, refusing to let anything back in. Theoretically, a black hole could even tunnel through space-time and emerge as a white hole somewhere else, creating a bridge between distant points in the universe, or even different universes entirely. But here's the catch: we've never seen one. No telescope has captured the telltale signature of a white hole's violent outbursts. Some researchers speculate that certain ultra-powerful gamma-ray bursts, those brief, brilliant flashes that outshine entire galaxies, could be white holes briefly flaring into existence before vanishing. Others propose an even wilder idea: that the Big Bang itself was a white hole event, the ultimate cosmic eruption birthing our universe from some unseen predecessor. Yet white holes face a major problem: they defy thermodynamics. Unlike black holes, which form naturally from dying stars, white holes would require some mechanism to reverse entropy, essentially making time flow backward at their cores. That's why many physicists argue they're mathematical curiosities rather than real cosmic objects. But the universe has surprised us before. If white holes do exist, they wouldn't just be oddities, they'd rewrite our understanding of causality, gravity, and the very structure of spacetime. Perhaps the most tantalizing possibility is that white holes aren't just theoretical, they're hiding in plain sight. Some models suggest that microscopic white holes could pop in and out of existence within quantum foam, those fleeting fluctuations in spacetime we discussed earlier. Others wonder if dark matter's gravitational effects might hint at white holes operating on scales we can't yet detect. Whether myth or reality, white holes force us to confront a humbling truth: the universe's rulebook might have chapters we haven't even glimpsed yet. And if they're out there spewing light, matter, and possibility into the void, they're proof that even the most extreme corners of physics still hold mysteries waiting to erupt. On an ordinary August evening in 1977, a radio telescope in Ohio picked up something extraordinary: a burst of radio waves so intense, so perfectly tuned to the frequency astronomers associate with interstellar signals, that the scientist reviewing the data circled it in red ink and scribbled, "Wow." Beside it, that single word named one of the most enduring cosmic mysteries: a 72-second transmission that came from nowhere, vanished without a trace, and has never been heard again. The wow signal wasn't just strong, it was suspiciously precise. It blared at exactly 1420 megahertz, a frequency hydrogen naturally emits, and one scientist had long theorized aliens might use to broadcast their presence. Picture tuning a radio through static and suddenly hearing a pure, unwavering tone, a deliberate hello from the cosmos. That's what researcher Jerry Amon experienced when he saw the signal spike on the printout, its intensity dwarfing the background noise of space. But by the time other telescopes swiveled to listen, the sky had gone silent. For decades, astronomers have chased explanations. Could it have been a comet's hydrogen cloud reflecting sunlight? A military satellite's stray transmission? The problem is, no natural phenomenon we know of matches the signal's unique fingerprint, its narrow frequency range, its sudden appearance and disappearance, its location in a seemingly empty patch of space near the constellation Sagittarius. Even the most skeptical scientists admit, if you wanted to design a signal to look artificial, this would be it. Yet the absence of a repeat performance haunts the search. SETI, the search for extraterrestrial intelligence, has scanned the same spot thousands of times, hoping for an encore. Some argue the signal's brevity suggests a one-time event, like a cosmic lighthouse beam sweeping past Earth. Others propose darker possibilities. What if it was a message, but the civilization that sent it met some catastrophic end shortly after? Or worse, what if they're still out there, waiting for a reply we never sent? The WOW signal's legacy isn't just about aliens. It's a reminder of how fragile our connection to the cosmos might be, a fleeting whisper in the static, easily missed if someone hadn't been listening at the right moment. And that raises a chilling question. How many other signals have we overlooked? The universe is vast, and patience isn't just a virtue. It might be the key to unlocking the greatest conversation in history. Among the countless stars dotting our galaxy, one stands out not for its brilliance, but for its bizarre behavior: KIC 8462852, better known as Tabby's star. Unlike most stars that shine with steady predictability, this distant sun in the constellation Cygnus flickers like a candle in the wind, dimming by as much as 22% at random intervals. That's not just unusual, it's unprecedented. Picture a light bulb that sometimes burns at full brightness, then suddenly drops to 78% power for days or weeks before flaring back up, all without any clear pattern. Astronomers have scoured the data, and nothing in their playbook fully explains it. The first instinct was to blame something ordinary, like a swarm of comets or thick clouds of interstellar dust passing between the star and Earth. But the numbers don't add up. For dust to block that much light, you'd need enough material to dwarf our entire solar system, and even then, the dimming wouldn't be this erratic. Comets, they might explain a single dip, but Tabby's star has had dozens, each with different shapes and durations. It's like trying to explain a thunderstorm with a single raindrop. That's when things got interesting. In 2015, astronomer Jason Wright floated a radical idea. What if we're seeing the shadows of something built? Specifically, a Dyson swarm, a vast network of energy collecting structures erected by an advanced civilization to harness their star's power. The concept isn't new. Physicist Freeman Dyson theorized back in the 1960s that a sufficiently advanced society might eventually surround its star with solar panels or habitats, creating a detectable signature. Tabby's star, with its strange, artificial-looking dimming, became the first serious candidate for such a megastructure. But before we start drafting first contact protocols, there's a catch. While the alien hypothesis grabs headlines, most scientists lean toward natural, if exotic, explanations. One leading theory suggests the star might be surrounded by a colossal ringed planet, like Saturn on steroids, with uneven debris casting unpredictable shadows. Others propose internal stellar activity we've never observed before, a kind of cosmic indigestion causing the star to hiccup light. There's even a chance we're witnessing the aftermath of a planetary collision, with leftover debris clouding the system. What makes Tabby's star so compelling isn't just the mystery, it's how it exposes the limits of our knowledge. Here's an object just 1,400 light-years away, practically in our cosmic backyard, and we're still scrambling for answers. Every time a new observation rules out one theory, two more spring up to take its place. The star's latest surprise, it's not just dimming erratically, it's fading overall, losing brightness year after year like a battery running low. Whether it's aliens, undiscovered physics, or something even stranger, Tabby's star reminds us that the universe loves a good plot twist. And as telescopes grow more powerful, one thing's certain: this cosmic enigma isn't done keeping us guessing. The deeper we look, the clearer it becomes. Sometimes the most fascinating discoveries aren't about what we find, but what we can't yet explain. And in that uncertainty, in those gaps between the data points, lies the thrill of exploration. Tabby's star isn't just a puzzle, it's an invitation to rethink what's possible. In the vast emptiness between the stars, where sunlight fades to a faint glimmer, two robotic explorers began behaving in ways that left physicists utterly baffled. NASA Pioneer 10 and 11, launched in the early 1970s to study Jupiter and Saturn, became famous for another reason entirely: their stubborn refusal to obey gravity's rules. As these spacecraft hurtled toward the edge of our solar system, mission controllers noticed something bizarre. Both probes were slowing down more than equations predicted, as if an invisible hand were gently pulling them backward toward the sun. This wasn't a tiny discrepancy. The Pioneer's deceleration, just 9 trillionths of a meter per second squared, might sound negligible, but over decades and billions of miles, it added up to a deviation of hundreds of thousands of kilometers from their expected path. At first, scientists assumed it was a simple glitch, perhaps thrust from leaking fuel or uneven heat radiation. But when they crunched the numbers, nothing in the probe's design could account for the anomaly. The effect was too consistent, too persistent, as though some fundamental law of physics had been subtly rewritten in the depths of space. Theories erupted like supernova. Could Einstein's theory of general relativity break down at extreme distances? Some researchers proposed modified Newtonian dynamics, or MND, a tweak to gravity's equations that might explain the Pioneer's behavior without invoking dark matter. Others whispered about exotic possibilities, hidden dimensions warping spacetime near the solar system's edge, or even the gravitational echo of parallel universes brushing against our own. For years, the Pioneer Anomaly became a rallying cry for those who believed our understanding of gravity was incomplete. Then, in 2012, a team of researchers offered a mundane but elegant solution. After painstakingly reconstructing the probe's heat signatures, they realized something surprising: thermal radiation from the Pioneer's plutonium power sources was reflecting off their antennae in just the right way to create a tiny but constant push backward. It wasn't new physics after all, just an overlooked quirk of engineering. Case closed, or so it seemed. But here's the twist: while the thermal explanation fits most of the data, a handful of scientists still argue the numbers don't quite add up. The deceleration was too uniform across both spacecraft, they say, and some aspects of the heat model rely on assumptions we can't fully verify. Could there still be a sliver of truth to the original mystery? The Pioneer's legacy endures as a cautionary tale, a reminder that even the smallest anomalies can reveal gaps in our knowledge, and that the universe often hides its secrets in plain sight, waiting for us to look closer. Deep in the constellation Eridanus, astronomers stumbled upon something that shouldn't exist: a sprawling cold spot in the cosmic microwave background, the afterglow of the Big Bang itself. Stretching nearly 2 billion light-years across, this frigid region is colder than its surroundings by a baffling 70 microkelvin. That might sound trivial, but in a universe where temperature variations are supposed to be smooth and predictable, this anomaly sticks out like a cosmic sore thumb. Dubbed the Eridanus Supervoid, it's one of the largest structures ever discovered and one of the most controversial. At first glance, the simplest explanation seems to be a void, an enormous, mostly empty region of space where matter is so sparse that light passing through loses energy, stretching to longer, cooler wavelengths in a process called the integrated Sachs-Wolf effect. Picture a marathon runner hitting a mile-long downhill stretch, their momentum bleeding away as gravity does less work. But here's the problem: the Eridanus Supervoid is too cold. Even the most extreme voids we've mapped don't account for the temperature drop observed. The numbers just don't add up. That's where things get wild. Some theorists suggest this might not be a void at all, but a cosmic bruise, evidence of a collision with another universe. In the multiverse hypothesis, our universe could be one bubble in an endless froth of realities, each with its own physical laws. If another bubble brushed against ours in the distant past, the clash might have left behind this eerie cold spot, a scar frozen in space-time. It's a radical idea, but the math holds. Such a collision could imprint exactly the kind of temperature anomaly we're seeing. Yet skeptics aren't convinced. They point out that the supervoid shape isn't quite right for a collision remnant, and alternative explanations keep bubbling up. One intriguing possibility involves cosmic textures, hypothetical defects in spacetime, like wrinkles in a crumpled sheet, formed during the universe's rapid expansion in its earliest moments. If one of these textures unraveled in the Eridanus region, it could have left behind a localized cold spot. Others argue it might be a statistical fluke, a rare but possible random fluctuation in the cosmic microwave background. But the cold spot refuses to be ignored. Recent observations reveal it's not just cold, it's structured, with concentric rings of temperature variation that deepen the mystery. If it were merely a void, those patterns shouldn't exist. The more we study it, the stranger it becomes, challenging not just our models of cosmic evolution, but the very foundations of cosmology itself. What makes the Eridanus Supervoid so thrilling isn't just its defiance of expectations, it's the reminder that even our most cherished theories about the universe are works in progress. Whether it's a fingerprint from another reality or a cosmic defect we've yet to understand, one thing's certain: the universe still has surprises up its sleeve. And that's what keeps us looking up. Imagine a cosmic monster with a magnetic grip so powerful, it could strip the electrons from your atoms while you're still thousands of miles away, turning you into a cloud of ionized particles before you even knew what hit you. This isn't some sci-fi horror scenario. It's the everyday reality near a magnetar, the universe's ultimate magnetic nightmare. Born from the collapse of massive stars, these neutron stars don't just have strong magnetic fields, they rewrite the definition of strong entirely. With fields measuring up to 10 quadrillion times more intense than Earth's, they're nature's most terrifying electromagnets, bending the very rules of physics into submission. What makes these stellar beasts so terrifying isn't just their strength, it's how that strength warps reality. Get within 1,000 kilometers of one, and its magnetic field becomes so intense that atoms stretch into needle-thin shapes, their electron clouds torn apart. Even the vacuum of space isn't safe. Quantum effects normally invisible to us get twisted into overdrive, creating bizarre distortions where light itself behaves unpredictably. But the real danger comes when these cosmic monsters get restless. Unlike ordinary neutron stars that spin predictably, magnetars occasionally suffer violent seizures known as starquakes, sudden cracks in their crust that release energy equivalent to billions of hydrogen bombs in a millisecond. The aftermath of these quakes is where physics textbooks get thrown out the window. In 2004, a magnetar 50,000 light-years away unleashed a blast so powerful it temporarily ionized Earth's upper atmosphere from halfway across the galaxy. The energy released in that single event outpaced our sun's total output for 100,000 years. And here's the chilling part: we still don't fully understand how that's possible. Current theories suggest these outbursts involve magnetic fields so twisted, they essentially tie themselves into knots before violently snapping, like a rubber band stretched beyond its limit. Yet magnetars aren't just destroyers, they're cosmic laboratories. Their extreme conditions let us test theories about quantum electrodynamics in ways no Earth-bound experiment could. Some researchers even speculate they might be sources of fast radio bursts, those mysterious intergalactic signals that have puzzled astronomers for years. And lurking beneath all these mysteries is an unsettling question. What happens when one of these magnetic titans decides to erupt a little closer to home? The universe has a way of humbling us, and magnetars are the ultimate reminder. They prove that even in a cosmos full of black holes and dark matter, there are forces at work far stranger and far more violent than we ever imagined. And as we keep searching the skies for their telltale flashes, one truth becomes clear. In the face of such power, our understanding of physics is still just scratching the surface. Just when we thought we'd mapped the edges of our own cosmic backyard, the solar system threw us another curveball, a place where the familiar scatter of icy rocks and dwarf planets suddenly drops off into nothingness. Out beyond Neptune and Pluto, past the realm of frigid worlds like Eris and Haumea, lies the Kuiper Belt, a sprawling disk of frozen leftovers from the solar system's birth. But here's where things get strange. Instead of tapering off gradually, the belt's objects vanish abruptly at about 50 astronomical units from the sun, as if someone drew a line in the cosmic sand and said, "No further." Astronomers call this boundary the Kuiper Cliff, and its existence defies everything we thought we knew about how planetary systems form. Theories about this sudden drop-off range from the plausible to the downright fantastical. The leading explanation, a hidden giant lurking in the darkness, Planet 9. This hypothetical world, estimated to be 5 to 10 times Earth's mass, could be shepherding the Kuiper Belt's outer edge with its gravity, sweeping up or flinging away objects that venture too close. Picture a massive, unseen hand rearranging the solar system's furniture, leaving behind only what it allows. But there's a catch. Despite years of searching, no one's spotted Planet 9 yet. Its existence is inferred from the odd clustering of orbits in the distant Kuiper Belt, a pattern that suggests something massive is pulling strings from the shadows. Yet some scientists argue the cliff might not need a planet at all. One alternative proposes that the Kuiper Belt's outer edge marks the spot where the protoplanetary disk, the swirling cloud of gas and dust that birthed our solar system, simply ran out of material. Think of it like a baker's dough that thins out at the edges. Beyond a certain point, there wasn't enough stuff to form more objects. Others speculate that gravitational tugs from passing stars in the sun's infancy could have stripped away the outer belt, leaving behind this sharp boundary. But the wildest ideas go even further. Could the Kuiper Cliff be evidence of a close encounter with another star long ago, one that stole away our solar system's outermost objects? Or more controversially, might it be a signpost of something even stranger, like the gravitational influence of a primordial black hole, a relic from the universe's earliest moments hiding in our own backyard? The possibilities are as thrilling as they are unsettling. What makes this mystery so compelling isn't just the what, but the why. If Planet 9 is real, why haven't we found it yet? If the cliff is natural, why don't other star systems show similar abrupt edges? Every new survey of the Kuiper belt deepens the puzzle, revealing a frontier that's anything but empty, just eerily quiet where we'd expect chaos. The Kuiper cliff doesn't just challenge our models of the solar system, it dares us to admit how much we still don't know about the place we call home. And until we solve it, one thing's certain: the universe's rulebook has a few pages we haven't even turned yet. Galaxies spin like cosmic carousels, their outer stars whipping around at speeds that should send them flying into the void, yet something invisible holds them together. This cosmic glue isn't stars, gas, or anything we can see. It's dark matter, the universe's most frustratingly elusive secret, outnumbering ordinary matter 5 to 1 and sculpting the cosmos on a scale we're only beginning to grasp. Picture a spiderweb where the silk is invisible, you can't see the threads, but you know they are there because everything else is caught in their grip. That's dark matter's role in the universe, an unseen scaffold shaping galaxies, bending light, and defying every attempt we've made to pin it down. The first clues emerged in the 1930s, when astronomer Fritz Zwicky noticed galaxies in the Coma cluster were moving too fast for the cluster's visible mass to hold them. It was as if an entire stadium crowd was cheering, but only a handful of voices could be heard. Decades later, Vera Rubin's observations of spiral galaxies confirmed the anomaly. Stars at the edges were orbiting just as fast as those near the center, violating Newton's laws unless some hidden mass was propping up the system. The conclusion was inescapable. Galaxies are wrapped in vast halos of something that doesn't emit, absorb, or reflect light. Something that interacts with the universe almost exclusively through gravity. But what is it? The leading candidate, WIMP, weakly interacting massive particles, are hypothetical subatomic entities that could permeate space like a ghostly fog, only rarely bumping into normal matter. Yet after decades of sensitive experiments in underground labs and space telescopes scanning for indirect signals, WIMP remain frustratingly theoretical. Alternative ideas keep bubbling up. Could dark matter be made of primordial black holes, forged in the universe's first chaotic moments? Or actions, ultra-light particles streaming through space like an intangible cosmic wind? Some theorists even propose we're chasing a mirage, that dark matter doesn't exist at all, and instead, gravity itself behaves differently on galactic scales, a theory called modified Newtonian dynamics, or MN. The stakes couldn't be higher. Dark matter isn't just some cosmic curiosity, it's the invisible architect of the universe. Without it, galaxies would never have clumped together in the early cosmos. Stars might not have ignited at all. Its gravitational fingerprints are everywhere, in the way galaxy clusters bend light like cosmic lenses, in the intricate web of filaments connecting the large-scale structure of the universe, even in the slight wobbles of stars caused by unseen masses tugging at them. Yet for all its influence, dark matter remains maddeningly aloof, a cosmic tease just beyond our reach. Here's what makes this mystery so thrilling. We're not just hunting for a particle. We're grappling with the possibility that 85% of the universe's matter belongs to a shadow realm we don't yet understand. Every null result in our detectors, every unexplained gravitational ripple, is a clue that the universe is playing by rules we haven't fully decoded. And until we do, one thing's certain: the cosmos is far stranger and far more mysterious than it appears. Even our most precise cosmic measuring sticks can't agree on how fast the universe is growing, and that disagreement might be the most exciting clue we've found in decades. Meet the Hubble tension, a stubborn discrepancy that's making cosmologists question whether we've missed a fundamental piece of reality. Here's the problem: when we measure the universe's expansion rate using nearby stars and supernova, we get one number. But when we calculate it by studying the ancient afterglow of the Big Bang, the cosmic microwave background, we get a value nearly 10% slower. That might not sound like much, but in a field where measurements are precise to decimal places, it's the equivalent of two clocks ticking at different speeds in the same room, and no one knows why. The most straightforward explanation would be an error in our measurements, but after years of cross-checking, both methods keep yielding the same conflicting results. That leaves us with something far more intriguing: the possibility that our understanding of the universe is incomplete. One leading theory suggests dark energy, the mysterious force accelerating cosmic expansion, isn't constant after all. Instead, it might be growing stronger or weaker over time, subtly tweaking the expansion rate in ways we haven't accounted for. Imagine blowing up a balloon where the rubber unpredictably changes thickness, sometimes stretching faster, sometimes slower. That's the kind of cosmic curveball we might be dealing with, but some physicists are exploring even wilder ideas. Could extra dimensions hidden from our perception be warping how we observe space's expansion? In string theory, these curled-up dimensions could influence gravity in ways that throw off our measurements. Or perhaps there's an unknown particle, a relic from the early universe, that's subtly altering the cosmic recipe. There's even a chance we're seeing echoes of a pre-Big Bang phase, a shadow of some deeper physics that set the universe's initial conditions. What makes the Hubble tension so electrifying isn't just the mystery, it's the stakes. If this discrepancy holds, it could mean rewriting textbooks on everything from particle physics to gravity. Every new observation tightens the knot. The latest James Webb Space Telescope data confirms the tension persists, ruling out more mundane explanations. We're left staring at a cosmic puzzle that refuses to be solved. And that's where the real magic happens, because when the universe contradicts itself, it's usually trying to tell us something extraordinary. In the vast emptiness between stars, where the distances are so great that light itself takes years to cross them, something unexpected streaked through our solar system, an object unlike anything we'd ever seen before. In October 2017, astronomers in Hawaii spotted a faint, fast-moving dot on their telescopes, tracing a path so extreme it could only mean one thing: this visitor wasn't from here. Named Oumuamua Hawaiian for scout, this mysterious traveler became the first confirmed interstellar object ever detected passing through our cosmic neighborhood. But what made it truly extraordinary wasn't just its origin. It was the way it behaved. At first glance, Oumuamua seemed ordinary enough, a reddish, rocky body about a quarter-mile long. But the closer scientists looked, the stranger it became. Its shape alone was bizarre, elongated like a cosmic cigar, spinning end over end in a way almost never seen in natural asteroids or comets. Then came the real shocker. As Oumuamua hurtled away from the sun, something inexplicable happened. It accelerated, as if pushed by an unseen force. Comets sometimes speed up due to outgassing, the heat of the sun vaporizing ice and creating a jet-like thrust. But Oumuamua showed no visible tail, no cloud of dust or gas that could explain its sudden burst of speed. It was like watching a car drive uphill with no engine. Theories erupted faster than solar flares. Some astronomers suggested it might be a rare type of hydrogen iceberg, a chunk of frozen hydrogen evaporating invisibly in sunlight. Others proposed it was a fragment of a shattered planet, ejected from another star system in some cataclysmic event. But the most tantalizing and controversial idea came from Harvard astrophysicist Avi Loeb, who argued Oumuamua's acceleration and odd shape could hint at something even more extraordinary: an artificial object, perhaps a light sail or probe from an alien civilization. Imagine a piece of technology designed to catch the momentum of starlight, drifting between the stars on currents of photons. Skeptics pushed back hard. Without definitive proof, they argued, attributing Oumuamua's behavior to aliens was premature. Yet even the more conservative explanations raised questions. If it was a comet, why no tail? If it was a bizarre new type of asteroid, why the unexplained acceleration? Every time one mystery seemed solved, another took its place. By the time telescopes could turn for a closer look, Oumuamua was already too far away, vanishing into the void as mysteriously as it arrived. What makes this interstellar enigma so compelling isn't just the unanswered questions, it's what Oumuamua represents. For centuries, we've wondered if we're alone in the universe. Now we have evidence that objects from other star systems can reach us. The next one might already be on its way. And when it comes, we'll be watching, because whether Oumuamua was a strange cosmic rock or something even more extraordinary, one thing's certain: the universe is full of surprises, and we've only just begun to notice them. Deep in the constellation Eridanus, astronomers stumbled upon something that shouldn't exist: a sprawling cold spot in the cosmic microwave background, the afterglow of the Big Bang itself. Stretching nearly 2 billion light-years across, this frigid region is colder than its surroundings by a baffling 70 microkelvin. That might sound trivial, but in a universe where temperature variations are supposed to be smooth and predictable, this anomaly sticks out like a cosmic sore thumb. Dubbed the Eridanus Supervoid, it's one of the largest structures ever discovered, and one of the most controversial. At first glance, the simplest explanation seems to be a void, an enormous, mostly empty region of space where matter is so sparse that light passing through loses energy, stretching to longer, cooler wavelengths in a process called the integrated Sachs-Wolf effect. Picture a marathon runner hitting a mile-long downhill stretch, their momentum bleeding away as gravity does less work. But here's the problem: the Eridanus Supervoid is too cold. Even the most extreme voids we've mapped don't account for the temperature drop observed. The numbers just don't add up. That's where things get wild. Some theorists suggest this might not be a void at all, but a cosmic bruise, evidence of a collision with another universe. In the multiverse hypothesis, our universe could be one bubble in an endless froth of realities, each with its own physical laws. If another bubble brushed against ours in the distant past, the clash might have left behind this eerie cold spot, a scar frozen in space-time. It's a radical idea, but the math holds. Such a collision could imprint exactly the kind of temperature anomaly we're seeing. Yet skeptics aren't convinced. They point out that the supervoid shape isn't quite right for a collision remnant, and alternative explanations keep bubbling up. One intriguing possibility involves cosmic textures, hypothetical defects in space-time, like wrinkles in a crumpled sheet, formed during the universe's rapid expansion in its earliest moments. If one of these textures unraveled in the Eridanus region, it could have left behind a localized cold spot. Others argue it might be a statistical fluke, a rare but possible random fluctuation in the cosmic microwave background. But the cold spot refuses to be ignored. Recent observations reveal it's not just cold, it's structured, with concentric rings of temperature variation that deepen the mystery. If it were merely a void, those patterns shouldn't exist. The more we study it, the stranger it becomes, challenging not just our models of cosmic evolution, but the very foundations of cosmology itself. What makes the Eridanus Supervoid so thrilling isn't just its defiance of expectations, it's the reminder that even our most cherished theories about the universe are works in progress. Whether it's a fingerprint from another reality or a cosmic defect we've yet to understand, one thing's certain: the universe still has surprises up its sleeve. And that's what keeps us looking up. Science fiction has long imagined the edges of galaxies as frontiers guarded by mysterious barriers, But what if reality is stranger than Star Trek ever dreamed? At the outermost fringes of our Milky Way, astronomers have detected a baffling phenomenon, a sprawling, invisible boundary that acts like a cosmic force field, repelling high-energy particles with inexplicable efficiency. Dubbed the Galactic Barrier, this enigmatic region doesn't just mark where our galaxy ends, it actively defends it, bending the rules of physics in ways we're only beginning to unravel. The first clues emerged when telescopes spotted an unusual excess of gamma rays and cosmic rays piling up along the Milky Way's perimeter, as if hitting an invisible wall. Normally, these high-energy particles, accelerated by distant supernova or black holes, should stream freely through interstellar space. Yet something at the galaxy's edge is deflecting them, creating a shock wave of radiation that glows faintly in our detectors. Imagine a river flowing toward a waterfall, only to hit an unseen barrier that sends the water splashing back upstream. That's the kind of cosmic traffic jam we're seeing, except on a scale spanning tens of thousands of light years. So what's creating this barrier? One leading theory points to the galaxy's magnetic fields, which might be woven into a protective halo at its edges. As particles approach, these tangled magnetic lines could act like a net, slowing and redirecting them. But there's a problem. The barrier's effect is far stronger than our models predict. Even the most intense magnetic fields we've observed shouldn't produce this level of deflection. That's led some researchers to speculate about more exotic explanations, like the presence of dark matter particles interacting in ways we've never detected, or even remnants of an ancient galactic collision that left behind a scar in spacetime. Then there's the eerie coincidence that's hard to ignore. The barrier's position aligns almost perfectly with the theoretical limit of our galaxy's gravitational influence. It's as if the Milky Way has carved out its own territory in the cosmos, marking its borders with an invisible, no trespassing sign. Could this be a natural byproduct of how galaxies form, or is there something more purposeful at work? The more we study it, the more the Galactic Barrier feels less like a fluke and more like a feature, a built-in defense system we're only now noticing. What makes this discovery so thrilling isn't just the mystery, it's the implications. If such barriers are common around galaxies, they could explain why the universe looks the way it does, shaping how energy and matter flow across cosmic distances. Or perhaps it's evidence of something even grander, a universal architecture far more intricate than we ever imagined. One thing's certain, the edge of our galaxy isn't just a quiet frontier. It's a battleground where invisible forces clash, and the rules of physics are still being written. High above our planet, hidden in the swirling dance of human-made satellites and space junk, lurks one of the most enduring cosmic mysteries, the Black Knight. This alleged 13,000-year-old alien satellite has fueled conspiracy theories for decades, with claims ranging from an ancient extraterrestrial observer to a shadowy government project. But peel back the layers of myth, and you'll find a story that's just as fascinating for what it reveals about our own fascination with the unknown. The legend began in the 1950s when amateur radio operators reported picking up strange, repeating signals from space echoes that seemed too rhythmic to be natural. Then came the grainy photographs, shadowy, angular shapes captured by early astronauts, said to be proof of an otherworldly craft silently circling Earth. The most famous image, often cited as the Black Knight itself, shows a jagged silhouette against the curve of our planet. But here's the twist. That photo was later identified as a thermal blanket lost during a 1998 space shuttle mission, drifting harmlessly in orbit. Yet the myth refuses to die, and for good reason. The idea of an ancient watchtower in the sky taps into something primal, a suspicion that we're not alone, and that the truth might be hovering just out of reach. Some theorists point to anomalous radar blips detected by early space agencies, while others cite Nikola Tesla's accounts of intercepting mysterious radio pulses in the late 1800s. Could these fragments add up to something real, or are we stitching together a cosmic Rorschach test from unrelated events? Science offers simpler explanations. Space debris, defunct satellites, and even ice crystals reflecting sunlight can create illusions of structured objects in orbit. The signals might have been early satellite tests or natural radio emissions distorted by Earth's atmosphere. But the human mind loves patterns, and the Black Night endures because it fits a narrative older than spaceflight itself, the idea that someone or something is watching. What makes this myth so compelling isn't whether it's true, but why we want it to be. In a universe that often feels indifferent, the thought of an ancient sentinel silently orbiting Earth gives the cosmos a touch of mystery, even kinship. And while the Black Night is almost certainly just a thermal blanket and a case of mistaken identity, its legend reminds us that sometimes the most intriguing space mysteries aren't out among the stars. They're the stories we tell ourselves about what might be lurking in the dark. Out in the cosmic jewelry box of the universe, where stars twinkle like scattered gems, there's one planet that puts even the most extravagant earthly treasures to shame. Meet Pioneer J1719-1438b, a world so dazzling it makes the crown jewels look like costume trinkets. This isn't just a planet. It's a celestial diamond forged in the crucible of a dead star's fury, orbiting its pulsar host with silent, sparkling defiance. The story begins with a violent cosmic transformation. Billions of years ago, this planet was likely a white dwarf, the dense, Earth-sized core of a spent star. But when its pulsar companion began siphoning away its outer layers, the intense gravitational pressure crushed what remained into something extraordinary, a crystalline behemoth composed largely of carbon compressed into diamond. Picture taking Mount Everest and squeezing it down to the size of a sugar cube, then repeating that process until the very atoms realign into a perfect lattice. That's the kind of extreme physics at play here. What makes this diamond planet truly bizarre isn't just its composition, it's how it behaves. Unlike any world in our solar system, Pioneer J1719-1438b orbits its pulsar in just 2 hours, a dizzying cosmic waltz that would vaporize most planets. The gravitational forces at work are so extreme, they've essentially turned this world into a celestial pendulum, its crystalline structure vibrating under the strain. Yet despite this relentless punishment, the planet endures, a testament to Diamond's legendary hardness on a scale we can barely fathom. But here's the real kicker: this planet shouldn't exist. Current models of planetary formation struggle to explain how such a dense, carbon-rich world could survive so close to a pulsar without being torn apart. Some theorists speculate it might be the lone survivor of a cannibalized star system, its siblings long since devoured by the pulsar's hunger. Others wonder if we're seeing the aftermath of a freak cosmic collision, where 2 white dwarfs merged and crystallized under impossible pressures. The implications stretch far beyond mere curiosity. If planets like this are common around pulsars, it means the universe has pockets of unimaginable wealth hidden in its darkest corners. A single fragment of Pioneer J1719-1438b, brought back to Earth, would dwarf the value of every diamond ever mined. But more than that, it's a reminder of nature's flair for the dramatic, a world where the rules of chemistry and physics conspire to create something both beautiful and bizarre. Yet for all its glittering allure, this diamond planet holds a darker secret. Its very existence hints at forces we've yet to understand, processes that twist matter into forms beyond our wildest imagination. And that's the true treasure here, not the diamond itself, but the realization that the universe is still full of wonders waiting to be uncovered, each one more extraordinary than the last. Among the grand tapestries of the cosmos, where galaxies weave into sprawling filaments and voids, one structure stands out not for its beauty, but for its sheer defiance of cosmic rules. The Hercules Corona Borealis Great Wall isn't just big, it's impossibly big, stretching an incomprehensible 10 billion light-years across. This gargantuan ribbon of galaxies and galaxy clusters dwarfs anything else we've discovered, so vast it shouldn't exist under our current understanding of the universe's architecture. The problem isn't just size, it's timing. According to the cosmological principle, the universe should look roughly the same in all directions on large scales, with matter distributed evenly once you zoom out far enough. Yet here's this titanic structure, a cosmic skeleton so enormous it spans nearly a seventh of the observable universe, flouting that rule entirely. Imagine drawing a map of Earth where one continent covered half the planet. That's the level of anomaly we're dealing with. What makes this discovery even more startling is how it challenges our models of cosmic evolution. In the aftermath of the Big Bang, tiny quantum fluctuations were stretched by inflation, seeding the gravitational wells that would eventually grow into galaxies and clusters. But the math suggests there simply wasn't enough time for gravity to sculpt something as colossal as the Hercules Corona Borealis Great Wall. It's like finding a skyscraper in the middle of the desert with no construction crew in sight. Nature doesn't build that big, that fast. Astronomers first stumbled upon this behemoth in 2013, while mapping gamma-ray bursts the violent deaths of massive stars. These brilliant flashes acted like cosmic breadcrumbs, tracing out a pattern that revealed the wall's staggering scale. But here's the twist: gamma-ray bursts are rare, meaning this structure could be even larger than what we've mapped, its full dimensions still lurking in the darkness between bursts. Theories attempting to explain it range from the cautious to the revolutionary. Some suggest it might be a chance alignment of smaller filaments, a trick of perspective like seeing faces in clouds. Others propose more radical ideas. Could this be evidence of a pre-Big Bang structure, a relic from some earlier phase of the cosmos? Or perhaps a sign that inflation, the universe's explosive growth spurt, wasn't as uniform as we thought, leaving behind wrinkles in spacetime on scales we're only now beginning to see. Then there's the unsettling possibility that our entire cosmic horizon is just a tiny patch of something far grander. If structures like this exist, what else might lie beyond what we can observe? The Hercules Corona Borealis Great Wall isn't just a curiosity, it's a challenge, a cosmic gauntlet thrown down to question everything we think we know about how the universe organizes itself. And until we solve its riddle, one thing's certain: the cosmos still holds mysteries too big for our textbooks. Imagine an engine that could propel spacecraft without fuel. No fiery exhaust, no bulky tanks, just pure thrust seemingly conjured from nothing. This isn't science fiction. It's the M-Drive, a concept so controversial it's been called the impossible engine. A device that appears to break one of physics' most sacred laws, Newton's third law of motion. For every action, there's an equal and opposite reaction, or so we thought. The M-Drive, a tapered metal chamber blasted with microwaves, allegedly generates forward momentum without expelling any propellant, like a car accelerating without its wheels touching the ground. The idea first emerged in the early 2000s, when aerospace engineer Roger Scheuer claimed his prototype produced measurable thrust. Skeptics scoffed. Physics textbooks practically screamed it couldn't work. Yet over the next decade, independent teams, including researchers at NASA's Eagleworks lab, reported similar results. Their experiments suggested the M drive wasn't just a fluke. It might be tapping into something fundamentally new. The numbers were tiny, a few micronewtons of force, barely enough to budge a grain of sand, but if real, the implications were staggering. A spacecraft equipped with such an engine could theoretically accelerate indefinitely, reaching distant stars without the need for colossal fuel reserves or gravity assists from planets. But here's where things get messy. The M drive's thrust is so minuscule, it's nearly indistinguishable from experimental error. Heat fluctuations, magnetic interference, or even seismic vibrations could mimic the effect. Critics argue that if the engine truly worked, it would upend centuries of verified physics, rendering conservation of momentum obsolete. Even Scheuer's explanations invoking quirks of relativity or quantum vacuum fluctuations strike many physicists as hand-waving at best. The scientific community remains deeply divided, with some dismissing it as modern alchemy, while others whisper about potential paradigm shifts. Yet the M drive's allure persists, and for good reason. History is littered with breakthroughs initially dismissed as impossible, from continental drift to quantum entanglement. Some theorists speculate the device might be interacting with dark energy or warping spacetime in ways we don't yet understand. Others wonder if it's a symptom of something deeper, a sign that our models of physics, while incredibly accurate, still have blind spots. Whether the M drive is a revolutionary breakthrough or a cautionary tale of measurement error, its legacy is undeniable. It forces us to confront a tantalizing question. Are there loopholes in the universe's rulebook waiting to be discovered? Until we know for sure, the M drive remains a ghost at the feast of physics, a reminder that even our most ironclad laws might have cracks. And in those cracks, perhaps, lies the future of space travel. Among the swirling chaos of dying stars and turbulent nebulae, one cosmic structure stands out with eerie precision: the Red Rectangle Nebula. Located about 2,300 light-years away in the constellation Monoceros, this celestial oddity defies the usual organic shapes of stellar death. Instead of the chaotic plumes or spherical halos typical of planetary nebulae, the red rectangle presents an almost mathematical perfection, two intersecting beams of glowing gas forming a near-perfect X-shape framed by a striking rectangular halo. It's as if an unseen cosmic architect drafted blueprints for this star's final act, leaving behind a structure so precise it borders on the artificial. The symmetry is so uncanny that early observers suspected an optical illusion. Yet high-resolution images from Hubble and other telescopes confirm this geometric marvel is real. At its heart lies HD 44179, a dying star in its final throes, shedding layers of gas into space. But unlike most stars that expel material in uneven bursts, this one seems to have orchestrated its demise with bizarre order. The leading theory suggests a dense disk of dust surrounds the star, funneling its ejector into two opposing cones that create the X-shape we see. But here's the puzzle. Disks around stars aren't rare, yet no other nebula exhibits this razor-sharp symmetry. Why does this one look like it was drawn with a cosmic ruler? One clue might lie in the star's binary nature. HD 44179 isn't alone. It's locked in a tight dance with a companion star, their gravitational waltz potentially shaping the outflow into such crisp geometry. Think of two skaters spinning while holding a ribbon between them. The forces they generate could twist the ribbon into precise patterns. Yet even this explanation feels incomplete, as other binary systems produce far messier nebulae. Some researchers speculate that magnetic fields, aligned in an unusually orderly way, might be sculpting the gas. others wonder if we're seeing the aftermath of a rare stellar collision, where the impact's violence somehow birthed this improbable symmetry. Then there's the nebula's color, a deep, unsettling crimson, unlike the usual blues and greens of similar objects. This hue comes from exotic carbon-rich molecules called polycyclic aromatic hydrocarbons, formed in the star's outer layers and glowing under ultraviolet light. These molecules are some of the building blocks of life, raising tantalizing questions about how such complex chemistry unfolds in the chaos of a dying star. What makes the Red Rectangle so mesmerizing isn't just its beauty, it's the way it blurs the line between nature and design. In a universe where randomness usually reigns, this nebula feels like a deliberate exception, a cosmic rebellion against entropy. And that's the real mystery here, not just how such precision emerged, but why we don't see it anywhere else. Is this a fluke of physics, or a sign that the universe has an artistic side we've only begun to notice? The Sombrero Galaxy has long been a showstopper of the cosmos, its broad, luminous brim of dust and stars making it one of the most recognizable celestial sights. But peer beyond its striking silhouette, and you'll uncover a far stranger secret. This galaxy isn't just wearing one halo, but two, each spinning in opposite directions like cosmic gears grinding against each other. It's as if the universe crafted a galactic Russian doll, nesting one mystery inside another, and astronomers are still scrambling to decode how such a thing could exist. Halos, those diffuse clouds of ancient stars surrounding galaxies, are supposed to be relics of a quieter, past remnants of galactic infancy that rotate sedately, if at all. Yet the Sombrero's dual halos defy that expectation with dramatic flair. The inner halo whirls in sync with the galaxy's disk, while the outer one spins backward, creating a celestial tug of war that shouldn't be possible under standard models of galactic evolution. Imagine two massive whirlpools stacked atop each other, one churning clockwise, the other counterclockwise, neither disrupting the other's flow. That's the level of cosmic contradiction we're dealing with here. So how did this bizarre configuration emerge? One leading theory points to a violent merger billions of years ago, where the Sombrero devoured a smaller galaxy. The gravitational chaos could have scrambled the orbits of stars, leaving some to orbit forward while others were flung backward. Think of it like pouring cream into coffee, stir one way, then abruptly reverse the spoon. The resulting swirls wouldn't blend smoothly, but instead create opposing currents. Yet even this explanation feels incomplete. Simulations show such mergers typically leave halos disordered, not neatly layered like the Sombreros. That's led some researchers to propose an even wilder idea. Dark matter might be pulling the strings. If the Sombrero's dark matter halo is oddly shaped, perhaps elongated or lopsided, it could twist the orbits of stars in ways we don't yet understand. Dark matter's gravitational influence is already known to sculpt galaxies in unexpected ways, but this would be its most audacious trick yet, orchestrating a celestial waltz where two stellar choirs sing in perfect, opposing harmony. Then there's the tantalizing possibility that we're seeing a snapshot of galactic adolescence. Most halos we study are ancient and settled, but the Sombrero's double halo might capture a rare transitional phase, a glimpse of how galaxies mature over eons. If true, it could rewrite our playbook for how structures evolve in the universe, revealing that even the quietest-looking galaxies might hide turbulent pasts. What makes this discovery so thrilling isn't just the puzzle, it's the reminder that even the most familiar cosmic landmarks can harbor jaw-dropping secrets. The Sombrero Galaxy has graced astronomy textbooks for decades, yet it's only now whispering its strangest story. And that's the beauty of the cosmos. No matter how much we think we know, the universe always keeps a few twists up its sleeve. Look up at the moon tonight, and you'll always see the same familiar face, those dark plains we call seas, the bright highlands, the craters frozen in time. But turn that thought around. The moon never sees us from the other side. This cosmic game of peekaboo isn't a quirk of perspective. It's the result of something called tidal locking, a gravitational ballet so precise it's left scientists marveling at its perfection. Tidal locking occurs when an orbiting body's rotation syncs perfectly with its orbit, like a dancer spinning just fast enough to always keep one side toward their partner. Gravity's pull creates slight bulges in both objects, and over time, friction slows the smaller body until its rotation matches its orbital period. The moon didn't start out this way. Billions of years ago, it spun freely. But Earth's gravity tugged harder on the near side, applying brakes until the moon's rotation locked into place like a clock with hands forever fixed. What's astonishing isn't just the mechanism, it's the timing. Our moon is the only major satellite in the inner solar system to be tidally locked to its planet. Even Mars's tiny moons tumble chaotically. Statistically, the odds of such perfect synchronization are staggeringly low, especially for a moon as large as ours relative to its host planet. That's led some to wonder, is this mere coincidence, or could tidal locking be a hidden ingredient for life? Consider the moon's role in Earth's story. Its steady gravitational pull stabilizes our planet's tilt, preventing wild climate swings that would render seasons unpredictable. The lunar tides may have churned Earth's primordial soup, stirring the chemical reactions that led to life. And that perpetually hidden far side, it shields us from solar radiation, its bulk acting as a cosmic umbrella. Without tidal locking, the moon's influence might have been erratic, a fickle partner rather than the steady anchor we've relied on. Yet the mystery deepens when we compare other systems. Exoplanet hunters have found worlds tidally locked to their stars, one side eternally scorched, the other frozen. But a moon locked to its planet with just the right mass and distance to nurture life, that's rarer than a solar eclipse. Whether by chance or some deeper cosmic logic, Earth's dance with the moon feels less like random physics and more like a carefully balanced equation, one we're only beginning to decode. Perhaps the most humbling thought of all, in a universe where chaos reigns, this single, silent lockstep has endured for eons. The moon's hidden face reminds us that even the most familiar celestial neighbors can hold profound secrets, and that sometimes the universe's most elegant tricks are the ones we take for granted. In the heart of the Tarantula Nebula, a cosmic tempest rages, a stellar nursery where stars don't just form, they explode into existence with terrifying grandeur. And at the center of this maelstrom lies R136A1, a star so colossal it redefines the word monster. Clocking in at 265 times the mass of our Sun, this behemoth shouldn't exist. According to every model of stellar formation, stars this massive should tear themselves apart before they even ignite. Yet there it burns, defiant, a cosmic rebel rewriting the rules of astrophysics right before our eyes. What makes R136A1 so baffling isn't just its size, it's the sheer violence of its existence. Imagine a furnace so intense, its radiation pressure should theoretically blow away the very gas that feeds it. That's the paradox at the heart of this star. Current theories suggest stars can't grow beyond about 150 solar masses without their own light ripping them apart. Yet R136A1 laughs in the face of those limits, shining with the brilliance of nearly 9 million suns. Its surface temperature soars above 50,000 degrees Celsius, and its solar winds scream outward at over 6 million miles per hour, enough to strip atmospheres from planets light years away. The discovery sent shockwaves through the astronomy community. Some researchers scrambled to explain it as a cosmic fluke, perhaps a rare merger of multiple massive stars. Others proposed that the Tarantula Nebula's uniquely dense environment allowed gas to pile onto the star faster than radiation could push it away, but the most tantalizing possibility: that our understanding of star formation is fundamentally incomplete. R136A1 might be the tip of the iceberg, hinting at an entire population of supermassive stars lurking in the universe's most extreme nurseries. And then there's the star's inevitable fate. Stars this massive live fast and die young, burning through their fuel in just a few million years. When R136A1 finally meets its end, it won't go quietly. It's destined for a hypernova, an explosion so violent it could outshine entire galaxies for weeks. The aftermath: likely a black hole with an appetite to match its progenitor's size, swallowing light and matter with the same indifference that R136A1 now radiates light. Yet for all its fury, this star's greatest legacy might be humility. It forces us to admit that the universe operates on scales we're only beginning to comprehend. In the grand tapestry of cosmic mysteries, R136A1 isn't just a thread, it's a blazing needle, stitching together new questions about how the most extreme objects in the cosmos come to be. And somewhere in another starburst nebula, another impossible titan might be waking up, ready to challenge our theories all over again. History books tell us the Middle Ages spanned roughly from the 5th to the 15th century, but what if nearly 300 of those years never happened? Enter the phantom time hypothesis, one of the most audacious alternate history theories ever proposed. In the 1980s, German historian Herbert Illich made a startling claim. The years 614 through 911 were entirely fabricated, inserted into the calendar by a conspiracy of medieval rulers and the Catholic Church. According to this fringe idea, we're not actually living in the 21st century. We're still in the early 1700s, and much of what we know about the Dark Ages is an elaborate fiction. At first glance, the theory seems absurd, but Illich and his supporters pointed to eerie gaps in the archaeological record, a lack of surviving buildings, documents, and even tree rings from this period. They argued Charlemagne, the legendary Holy Roman Emperor, might have been a fictional character invented to fill the phantom centuries. Even the Gregorian calendar reform in the 1500s, which adjusted dates to correct drift, was framed as evidence of tampering. The hypothesis suggests this grand temporal forgery was orchestrated to legitimize power grabs, with rulers literally rewriting history to extend their reigns or claim ancient lineages. Mainstream historians have thoroughly debunked these claims. Radiocarbon dating, astronomical records, and cross-referenced chronicles from China and the Islamic world all confirm the timeline. The missing artifacts blame the chaotic upheavals of the era, Viking raids, shifting empires, and the simple decay of time. Yet the phantom time hypothesis endures, less as credible scholarship and more as a provocative thought experiment. It forces us to confront how fragile our grip on history really is. Most of us take chronology for granted, trusting that the past is as solid as the dates in textbooks. But this theory whispers an unsettling question. What if the scaffolding of time itself isn't as stable as we assume? Consider how timekeeping has evolved. Early calendars were tied to harvests or rulers' reigns, not atomic clocks. The Julian calendar, used for over 16 centuries, accumulated 10 days of drift before the Gregorian correction. Even today, we debate whether the Holocene epoch has ended and the Anthropocene begun, proof that eras are as much human constructs as natural phenomena. In a universe where black holes warp time and quantum particles seemingly ignore it, the phantom time hypothesis, however outlandish, taps into a deeper truth. Time is far stranger than our neat calendars suggest. So while we can safely dismiss the idea of missing centuries, the theory's legacy lingers. It reminds us that history isn't just a record, it's a story shaped by the biases and blind spots of those who wrote it. And in a cosmos where time bends and stretches, perhaps the most valuable lesson is humility. The past may be set in stone, but our understanding of it is always, inevitably, a work in progress. If there's one number that keeps physicists awake at night, it's one followed by 120 zeros. That's the staggering discrepancy between quantum physics' prediction of vacuum energy and what we actually observe in our universe, a mismatch so colossal it's been dubbed the Vacuum Catastrophe. At its heart lies a battle between two titans of modern science: quantum mechanics, which governs the impossibly small, and cosmology, which charts the impossibly large. And right now, they're giving us completely different answers about the very fabric of space itself. Quantum theory tells us that empty space isn't truly empty. Even in a perfect vacuum, particles flicker in and out of existence, their fleeting energy creating what's known as zero-point energy. When physicists calculate the cumulative effect of these quantum fluctuations, the numbers spiral out of control, predicting a vacuum energy density so intense it should have ripped the universe apart moments after the Big Bang. Yet when we measure the actual energy of empty space through cosmological observations, it's almost laughably weak, like comparing the power of a supernova to a candle flame. That 120 order of magnitude gap isn't just a rounding error. It's the largest mismatch between theory and observation in all of science. So where does this leave us? One possibility is that our understanding of quantum field theory is fundamentally incomplete. Maybe there's a cancellation mechanism we haven't discovered yet, some elegant symmetry that perfectly balances the books. String theorists have proposed hidden dimensions could absorb this excess energy, while others suggest exotic particles might mediate the difference. But the wildest idea, that we're seeing evidence of a multiverse, countless universes with different vacuum energies, and we just happen to inhabit the rare one where the numbers are survivably low. Yet the vacuum catastrophe isn't just a theoretical puzzle, it's a crisis with cosmic stakes. Vacuum energy shapes the expansion of the universe, and even tiny changes would make life impossible. If the predicted value were correct, galaxies would never have formed. Space would have expanded so violently that matter couldn't clump together. This razor-thin balance between prediction and reality forces us to confront an unsettling question. Are we missing a universe-sized piece of the puzzle, or is nature playing by rules we haven't even imagined? What makes this anomaly so profound isn't just the math, it's what it reveals about our place in the cosmos. The vacuum catastrophe humbles us. It shows that even our most sophisticated theories can brush up against the limits of human understanding. And somewhere in that yawning gap between calculation and observation, between the quantum and the cosmic, lies the next great revolution in physics, waiting to be uncovered. From voids so vast they defy cosmic architecture to planets forged from celestial diamonds, these 30 wonders remind us that the universe operates on a scale far beyond human intuition. Each anomaly we've explored isn't just a curiosity, it's a crack in the facade of our understanding, revealing how much we still don't know about the forces shaping reality. Take the eerie silence of the Boötes Void, where galaxies should thrive but don't, or the hypnotic spin of neutron stars, where a teaspoon of matter outweighs mountains. These aren't just scientific puzzles, they're invitations to imagine bigger. Consider how these mysteries reshape our perspective. The Great Attractor's unseen gravitational pull reminds us that even the mightiest forces can remain hidden, while quantum foam's seething energy hints at a subatomic chaos beneath the calm surface of empty space. And what about Tabby's star, flickering like a malfunctioning streetlight across the cosmos? Whether it's surrounded by alien megastructures or natural phenomena we've yet to discover, its erratic behavior challenges us to reconsider what's possible in stellar evolution. What ties these phenomena together isn't just their defiance of physics, it's how they expose the limits of our current knowledge. The Hubble tension's conflicting expansion rates might point to dark energy's evolving nature, while the Galactic Barrier's particle-deflecting edge suggests entire chapters of astrophysics waiting to be written. Even the humble moon, locked in eternal sync with Earth, poses profound questions about cosmic coincidences and the delicate balance that makes life possible. The real magic lies in how these enigmas connect. Magnetars warp spacetime with magnetic fields strong enough to atomize you from light years away, while the M-drive's controversial thrust, should it prove real, could rewrite Newtonian mechanics. The universe doesn't just bend rules, it invents new ones in real time, leaving us scrambling to keep up. And that's the thrill of exploration. Every answered question reveals 3 new mysteries, each more bewildering than the last. So as we close this journey through physics' greatest rebels, remember the cosmos isn't just stranger than we imagine, it's stranger than we can imagine. Which of these phenomena leaves you awestruck? Is it the haunting whispers of the wow signal, or the mathematical perfection of the Red Rectangle Nebula? Drop your thoughts below, and if you've enjoyed this dive into the universe's rule-breaking spectacles, hit subscribe. Because in a reality where white holes might spit out matter and entire centuries could be missing from history, one thing's certain: the next cosmic revelation is always just over the horizon. What if everything we've explored, the cosmic voids, the rebellious stars, the mysterious forces bending space-time, aren't just quirks of nature, but glitches in something far stranger? The simulation argument takes our journey through physics anomalies and flips it on its head, proposing that our universe's most baffling features might not be bugs at all, but intentional lines of code in an unfathomably advanced cosmic program. Think about the uncanny precision of our universe's constants. Gravity's strength, the speed of light, even the charge of an electron. Tweak any of these values by a fraction, and stars wouldn't ignite, molecules couldn't bond, and life as we know it would be impossible. This fine-tuning has long puzzled scientists. Is it sheer luck, or could it be the signature of a universe deliberately calibrated to allow complexity? Futurists like Nick Bostrom argue that if civilizations eventually develop the power to simulate conscious beings, the number of simulated minds would vastly outnumber biological ones. Statistically, we're more likely to be artificial intelligences in some higher realities, quantum computer, than flesh and blood beings in a base universe. But the clues don't stop at fine-tuning. Consider quantum mechanics' inherent weirdness: particles that exist in multiple states until observed, as if rendering only what's needed to conserve processing power. Or the pixel-like limit of Planck length, below which space loses meaning, reminiscent of a digital resolution. Even the Fermi paradox takes on new meaning. If we're in a simulation, the eerie silence of the cosmos might simply mean other civilizations weren't coded into our instance. Critics dismiss this as unfalsifiable metaphysics, but proponents counter that certain discoveries could support the hypothesis. Finding mathematical artifacts in cosmic background, radiation repeating patterns, or anomalous symmetries might hint at underlying code. Some even suggest that if we ever attempt to create our own universe simulations, it would ironically boost the odds that we're already inside one. Whether you find the idea exhilarating or unsettling, the simulation argument serves a deeper purpose. It challenges us to question the nature of reality itself. framing physics' greatest mysteries not as problems to solve, but as breadcrumbs left by an unimaginable architect. And that's the ultimate takeaway from our journey through the universe's rule breakers. The cosmos isn't just stranger than we imagine. It might be stranger than we can imagine, whether it's written in equations or lines